Welcome to The Explainer. Today we're going to break down one of the most fundamental building blocks of the Go programming language, functions and methods.
Okay, so these are the big ones, right? Function or method, value or pointer. I don't care if you're just starting out or you've been doing this for years. Every Go developer bumps into these questions. But don't worry, by the end of this explainer, you're going to have this stuff down cold.
So here's our game plan. We'll start with the core distinction, then move to an unlocking principle, a powerful consequence of that, a really critical choice you have to make, and finally we'll look at the extended toolkit. Let's jump right in.
All right, section 1, the core distinction. Let's really nail down the difference between functions and methods, once and for all.
Okay, a function. What is it, really? It's just a standalone block of code. It's not tied to anything in particular. The analogy here is perfect. It's like a public telephone. Anybody can walk up and use it. It's a general-purpose tool.
Now, a method, that's a whole different beast. A method belongs to a specific type. It's attached to it through something called a receiver. So think of it like a personal skill. If you have a person type, speaking is a skill that person has. You wouldn't just shout, "speak," out into the void. You'd say, "this person.speak."
And you can see this difference plain as day in how you call them. For a function, you call it from its package, right? Like fmt.println. But for a method, you call it on a variable. It's myVariable.doSomething.
So let's just boil it all down. The key word here is association. Functions are standalone for general utility. Think fmt.println. It'll print pretty much anything you throw at it. Methods, though, are all about actions on a specific type's data. You've got a circle? You call myCircle.area to get its area. See the difference? One's general, one's specific.
Okay, section 2. This next part is, well, it's a real game changer in Go. It's what unlocks so much of the language's power. We're talking about functions as first-class values. You'll hear this term first-class citizens a lot. All it really means is that you can treat a function just like any other piece of data. Seriously, you can stick it in a variable, pass it into another function as an argument, or even have a function return it as a result, just like you would with an integer or a string. Check this out. This is the simplest way to see it in action. We're creating a function right here on the spot. It doesn't even have a name, which is why we call it an anonymous function. And we're just assigning it to the variable f. That's it. Now the variable f is a function, ready to be called whenever we want. Now, here's a tip for when you start writing more complex code, something senior engineers do all the time. You can actually define your own function type. Look at this operation type. It's just an alias for a function that takes 2 ints and returns an int. Why do this? It makes your code way more readable, especially when your function signatures start getting complicated.
All right, section 3. Because we can treat functions like values, we get this amazing side effect, a really powerful consequence called a closure. This is seriously cool stuff.
Okay, so what on earth is a closure? It's basically a function with a memory. It remembers the variables in the environment from where it was born, even long after its parent function has finished running. It kind of closes over those variables, hence the name.
I love this analogy. Think of a normal function as a traveler. A closure is a traveler with a magic backpack. Inside that backpack are variables from its hometown, the function that created it. And here's the key. It carries that exact same backpack on every single trip. So whatever it puts in or takes out, the changes stick.
Let's make this real. Look at this counter function. It does 2 things. It creates a local variable called count, and then it returns another function. That function it returns is our closure, and it has closed over that count variable, meaning it now has exclusive private access to it.
So let's say we create a counter called increment a. The first time we call it, what happens? It reaches into its own little backpack, finds the count variable, which was 0, adds 1 to it, and now it's 1. And when we call it again, it doesn't start over. It remembers. It goes back into that same backpack, sees the count as 1, adds 1, and now it's 2. Its state is preserved between calls.
Okay, but here's the million-dollar question. What if we call that counter function again and make a totally new one? Let's call it increment b. Is it going to share the same backpack with increment a? Are they connected at all?
Absolutely not. When we created increment b, it got its own brand new, completely separate backpack with its own count variable inside. So when we call it for the first time, it starts from 1. This is a beautiful, simple example of data encapsulation. Each closure has its own private state.
Okay, let's shift gears. We're going back to methods, because there's a critical choice you have to make literally all the time when you're writing them: value receivers versus pointer receivers.
This is one of the best analogies in programming, I think. A value receiver, it gets a photocopy of the data. You can scribble all over that copy, do whatever you want. The original document is safe and sound, untouched. But a pointer receiver, it gets the original document. You make a change, it's permanent. That's the whole deal.
So how do you pick? It's actually a really simple checklist. Question 1, and this is the big one. Do you need to change the data? If the answer is yes, stop right there. You have to use a pointer. No choice. Okay, if the answer is no, then you ask question 2. Is this thing I'm passing really, really big, like a huge struct? If yes, you should probably still use a pointer just to be efficient and avoid making a giant expensive copy. If the answer to both of those questions is no, a value receiver is totally fine.
And here's the real pro tip, the thing that makes your code feel, well, idiomatic, like real Go code. It's all about consistency. The rule of thumb is this: if any method on a type needs a pointer receiver, just make them all pointer receivers. Don't mix and match. It keeps your code predictable and saves the next developer a lot of headaches. Trust me.
All right, last section. Let's do a quick lightning round of a few other cool, advanced tools in your Go function toolkit.
Okay, first up, variadic functions. See those 3 dots? That's your clue. It basically means and any number of other things. It lets you write super flexible functions like fmt.println that can take 1 argument or 10. Next, named returns. This is where you actually name your return values right in the function signature. It's awesome for clarity. It's like self-documenting code. And finally, the special init function. This is a function with a superpower. It runs automatically, all by itself, before your main function even starts. It's the perfect spot to do setup stuff, like establishing a database connection.
So look, at the end of the day, all these things, methods, closures, pointer receivers, they aren't just syntax. They're tools. They're patterns for thinking about how to structure your code. So the real question to leave you with is, now that you've got this toolkit, how are you going to go back and make your own code more efficient, more expressive, more Go? Thanks for joining this explainer.